we use only the N and L quantum numbers. And rather than the integer that we use for L when writing a set of quantum numbers, we're going to use the letter designations that we're accustomed to. So rules to follow. 1. The electrons tend to fill orbitals in order of increasing energy. Increasing energy. So we start filling the lowest orbitals and then add electrons to subsequent subshells and orbitals as we add electrons. Number 2 is based on the Pauli exclusion principle, and that is each orbital holds a maximum of 2 electrons. Okay, and also Hund's rule, and that is when orbitals of equal energy are filling, or when filling orbitals of equal energy, we place 1 electron in each orbital with the same spin. Before we pair with the opposite spin, or before pairing electrons with the opposite spin. Okay, so I'm just going to summarize some of what we saw when we were talking about quantum numbers, and so I'm going to just make a little table. Value of L, I can go from 0, 1, 2, 3, 4, 5, and on, theoretically. The letter designation that corresponds to these L quantum numbers that we will use in the configurations, or electron configurations, are S, P, D, F. Now, we only have discovered elements that contain electrons in the F subshells. However, theoretically, we also have G, H, we have 6 here, we would have I, J, so forth, okay? I'm also going to relate this to M sub L. So M sub L, remember, describes the orientation of orbitals in space, but we can use the value of M of L, 2 times L plus 1, to give us the number of orbitals in that subshell. And for L equals 0, there's only 1. There's 3 in the P, 5, 7. Theoretically, G would have 9, H 11, and so forth. And then the maximum number of electrons in a subshell, we know that each orbital contains 2 electrons. So if we have one orbital, the maximum number of electrons in that subshell is 2. We have 3 orbitals in a p subshell, max number of electrons in that subshell is 6. This is 10, 14, 18, 22, and so on. Okay, so now let's write some electron configurations and draw their corresponding orbital diagrams. And we're going to look at potassium, I hope, first, with an atomic number of 19. So it has 19 electrons in the neutral atom. Excuse me. The electron configuration starts always at 1s. And if you look at the periodic table, you'll see that potassium is in row 4, so n equals 4, and it is in row 1 as well. So it has 1 valence electron. So there's only 1 electron in that s orbital. So our configuration is going to start with 1s2, and we're going to go all the way up to 4s1. So that's the last word in our sentence. So we have 1s2, 2s2, 2p6. We're following the periodic table, going across each row, doubling back and going to the next. We have 3s2, 3p6, 4s1. This is the last electron in that potassium atom. It is the valence electron. Okay, so valence electrons occupy the highest n level. So there's 1 valence electron for potassium, and in fact there's only 1 valence electron for any element that is in group 1a. They all have 1 valence electron. What distinguishes them from one another is the principal energy level. Okay, so that's the electron. Actually, let me point out something else. So this is the valence electron, and there are other elements obviously have more valence electrons. The term that applies to these other electrons, these are called core electrons. So the sum of the core and the valence electrons have to add up to 19. Now let's draw the orbital diagram. So we have to have a 1s box, we have to have a 2s box, we have to have a 2p box, 3s box, 3p box, and the 4s orbital box. All electrons up to the 4s are paired. We have an unpaired electron here. So I put 1 electron in each orbital before I start pairing. Oops. Come on. Sorry, to make those big enough there. You could have placed that electron in the down position for a negative spin. Doesn't matter, as long as when you're filling orbitals in the same subshell, they initially each subshell or each orbital gets an electron with the same spin before you start pairing. So now let's look at the potassium ion. So potassium being in group 1A with that one valence electron loses one electron to form the K plus ion. And the electron that is lost is that 4s electron. So its electron configuration, so this would have 18 electrons, is that group of electrons that were the core electrons. So this is the electron configuration for the potassium ion. And of course, if we drew the orbital diagram, it would be represented just by this part. So you lose or loss of the 4s valence electron to form that ion. Now let's take a look at the electron configuration of argon, a noble gas. It has 18 electrons. So its electron configuration is the same as the potassium ions, or it would be more correct to say that the potassium ion's electron configuration is the same as that of argon. And there is a name for this phenomenon, and it is, we'd call these species electronic. So if an element of an atom or ion has the same electron configuration of another element or ion, they are considered to be isoelectronic with one another. Okay. And so this is also what drives the formation of ions, and that's the stability of the electron configuration of a noble gas. So when metal atoms lose electrons, they're doing so to obtain the electron configuration of a noble gas, and when nonmetals gain electrons, they're doing so to also obtain the electron configuration of a noble gas. And we'll see that in the next example, because now we're going to look at chlorine with 17 electrons. So if you locate chlorine on the periodic table, it's in row 3. So the last principal energy level is 3, and it is in group 7A, so it's in a P, the 3P subshell. So, and it's in 7A. So the last word in our electron configuration is going to be 3p5. So I start with 1s2, 2s2, 2p6, 3s2, 3p5. How many valence electrons do I have? These are the valence electrons. So there are 7 valence electrons. That is also given by the Roman numeral at the top of that column. Tells us how many valence electrons there are. These are the core electrons, of which there are 10. Okay. Orbital diagram for chlorine, we need a 1s, a 2s, 2p, 3s, 3s, and the 3p. All orbitals below the 3p are completely filled. But when I get to the 3p, I'm going to put 1 in each orbital before I start pairing. So there is 1 unpaired electron in chlorine. We know then it would be paramagnetic because it has an odd number of electrons. Now, the nonmetals form ions by gaining electrons. And what the driving force of that, of course, is what we've just talked about, the fact that they will gain the electron configuration of a noble gas when they gain those electrons. So the chloride ion has 18 electrons. So it fills that 3p, or that addition of that electron fills that 3p subshell. So now we have 3p6, and we saw that this is also the electron configuration of argon. So we can say that potassium and chloride ions, potassium and chloride ion, are isoelectronic. With argon. They have the same electron configuration. Okay, let's see. I think we're gonna flip. Actually, maybe, yeah, no, let's go to the next slide. I want to take a look at some transition metals, or one transition metal. No, we're going to look at a couple. So we do know that transition metals can carry a variety of charges depending upon the identity of that particular metal. We're going to look at cobalt. The neutral atom has 27 electrons, and the electron configuration for cobalt is 1s2, 2s2, 2p6, 3s2, 3p6. We hit row 4, fill the 4s, and based on what we know about the overlap of energy levels, when we hit row 4 and the transition metals, we hit the 3D subshell. So the D subshells, or the N value for the D subshells, are determined by the row number minus 1. Okay? So if we're in 4s, the D subshell is in N equals 3. And we have 7 electrons in that D subshell. Okay, so let's talk about two things here. An abbreviated electron configuration And how we write that, and some other terms as we're describing these electrons. So first, how many valence electrons does cobalt have? 2. Highest N value only. So cobalt has 2 valence electrons. And if it has 2 valence electrons and a total number of electrons of 27, then it has 25 core electrons. When we write an abbreviated electron configuration, we identify the previous noble gas to the element in question. And for cobalt, what would that be? Oh, I don't have the periodic table right here in front of me. And I don't remember. I think it's neon, but no, argon. Okay, it was argon. Sorry about that. Okay, so to write this in an abbreviated electron configuration, previous noble gas, argon, in brackets, followed by the remainder of the electron configuration. Okay. So there are terms to describe the electrons used, or the notation and part of the configuration used in the abbreviated electron configuration. These represent the noble gas symbol in brackets represents the inner electrons, and these then are the outer electrons. So we have then, what do we have? 18 inner electrons and 9 outer electrons. So inner and outer mean different things when we're talking about an abbreviated electron configuration versus valence and core electrons. Okay, so cobalt forms a 2+ and a 3+ ion. So let's look at the electron configuration of the 2+ ion first. 2 electrons are lost to form that 2+ ion, and the 2 electrons that are lost are in the outermost or highest energy level. So those 4s electrons are lost first. So the electron configuration for cobalt 2+ is this. Okay, these electrons were lost, the valence electrons. Now, when the 3+ ion is formed, we lose an additional electron, and that comes out of the 3D subshell because it is now the highest level of energy. Okay. So the configuration for cobalt 3+, 1s2, 2s2, 2p6, 3s2, 3p6, 3d6. Okay? Valence electrons last first.